27.
Ну да.
Сакраментальный вопрос, является ли 57 простым числом?
И это на 3 делится.
А?
На 3 делится.
Правильно, а еще на что? А?
Еще на 19.
Вот здесь просто если чистить все.
Чего? О,
А ты знаешь, где власть? Но ты его исправишь?
Боже, там кто-то тоже может?
Ну, сейчас ты напишешь, я просто не смогу.
И запись даже будет. И запись будет.
Мне кажется, спам.
Я знаю, что это. Нужно сильно нажать, это искусство. Чтобы загорелся такой вот кругок. Видишь, у меня такой выходит? Немножко страшно поначалу. О, видишь? Значит, талантливый.
А кого?
Ну, раньше были проблемы с стиранием красок.
Я ходил в какой-то семинар, не помню, не важно.
В какой-то момент на этом семинаре он очень гордо вышел в доске и сказал, ну, когда ты писал? Я сегодня на доске писать не буду. Мне разрешили надеть парадный пиджак. Понятно, что парадный пиджак не может быть не человек, который стоит у доски. Видишь? Немец хитер, обезьяну выдумал. Ну, удачного вам матрицу 2 надо.
Let's start. Last time we classified representations of this group P. Is it supposed to be red? It's fine with me, but
Probably you can change it in color plane.
here? Here.
Maybe just.
No?
Yeah.
Здесь как бы, ну сейчас
No, it's fine with me. Okay.
Ну ладно, да. Ничего, что здесь будет одна программа, а там другая, просто вот на том уровне.
Программа?
Ну да. Сейчас, секунду.
О! Может, не надо было?
Не, сейчас. Я просто открыл вот как бы просто.
О, Господи. А красный-то был ничего сам по себе.
Ну, да.
Он мне настолько мешал, что
Да.
все сворачивается.
Давайте как раньше и красный. Я не против.
Не знаю, нет, просто вот это как бы просто как отключает, как компьютер будет просто как доска. То есть здесь
А здесь двигать нельзя будет, да, получается?
двигать нельзя, это просто как доска.
А потом нужно будет что-то такое стереть, да, все?
Ну да.
Ну там, как я понимаю, можно одной кнопкой все очистить.
Да.
Что, сюда надо?
Ну все.
А это так и будет всегда?
Ее можно
Можно
подвинуть.
подвинуть. Да, если можно.
Да? Я всегда не будет.
Ну, я не знаю, было бы... Нет, она сейчас... О, стирать можно.
Стирать можно?
Еще дальше. А попробуйте стирать вот за части. Сделать.
Нет.
Нет.
Ну, хорошо. So let's start, try to start once again. So I have this subgroup, upper triangular, A, B, 0, 1.
Ну, я думаю, что можно иконки на экране убрать, чтобы они
как?
скинули.
Да, это
Как?
не то, что вы просто, мне
А здесь
кажется.
нет компьютера, да? Ладно.
Да ладно, давайте просто продолжим.
And last time we classified its representations. So there was a lot of characters. And there was one dimension of representation, representation of dimension q minus 1 that started with your forward. Okay, and now the Borel subgroup of upper triangular matrices is the product of P and direct product of P and the center. You have the scalar matrices. And so the representations are just products of the characters of the center and the representations of P. So for example, there will be now Q minus 1, irreducible representations of dimension Q minus 1. Okay, but we will only need the characters of Borel. So we fix two characters from the multiplicative group to complex numbers, and then mu of A, B, 0, D will be, just definition, mu1 of A times mu2 of mu2 of B. Yes.
Why there is no other irreducible character, irreducible representation that one-dimensional for Borel?
No, there's a lot of, there's like a Q minus 1 squared one-dimensional representation. I mean the characters.
Yeah.
These are all the possible characters. They are trivial on this unipotent upper triangular, strictly upper triangular subgroup.
Okay. And we want to prove that that's all of them. No.
Yes, it's certainly because well, all the characters they factor through the abelianization model commutant. The commutant is this strictly upper triangular subgroup, and the quotient is just diagonal matrices. So it's all very elegant. Okay, and then we had this element W. 0, 1, 1, 0 in GL2, and certainly if we conjugate with W, the Borel goes to the lower triangular matrices, but the Cartan, that diagonal matrices, they stay diagonal, but they switch, and so we define mu W as mu2, mu1. Just for shortcut. Okay, so now we'll study the so-called principal series. Representations of G, that's G of 2. Q. And well, there is some slight divergence in terminology. Well, first of all, they are induced from Borel to GL from some character mu, and well, the how to say it? We will denote it like this. So there will be some vector space, and the direction will be denoted mu hat. And we will eventually prove later on today that this induced representation is already irreducible if this character is not degenerate. That is, mu1 is not mu2. So let me formulate our goal for today. So mu1 is not mu2 implies that this mu hat is irreducible. And then it is certainly called principal series. But if mu1 equals mu2, then this induced representation you had decompose into the sum of two. One is just the character mu, well, 1 or 2 of determinant of G. So it's one-dimensional, plus another which is called Steinberg number mu. These are irreducibles. By the way, here dimension is q plus 1, and here dimension is 1, and here q. Okay, and now, well, probably nobody calls the one-dimensional characters the principal series, but some people call those two-dimensional things principal series. But say over other fields like real or periodic, they will not be called principal series, they will be called discrete series. So there is some divergence in terminology. Apart from those, there is also something, some representation called cuspidal, and they have dimension q minus 1. Maybe we'll have time for this today, or maybe next time.
All the remaining
Representations are cuspidal, and their dimension is q minus 1. Okay, and well,
Irreducible representation.
yes, irreducible, yes. And while on the trailer, I can say that those guys restricted to p will be just isomorphic to pi, to this pi. Okay, so now let's go slowly and let's first prove, well, maybe introduce an important concept and prove our first lemma. Okay, so for any representation, whatever v rho of GL of our group, we define the Jacquet functor JV. Sorry. This is the coinvariance of U. So U was mentioned but never written down. The upper triangular subgroup. So they're coinvariants. And since all our representations are over the coefficient field of complex numbers, they are all semi-simple, and the coinvariants are the same as invariants. But say again over the local fields, periodic or reals, the invariants will make no sense. They will be just zero, and one has to work with coinvariants. So this is the correct definition. But over the finite field, this is the same as invariants. Okay. Now, certainly the unipotent group U acts trivially on its own invariants or coinvariants, but the normalizer of U, which is the Borel subgroup, acts non-trivially. But then the subgroup U inside B acts trivially, so this action factors through the quotient. Maybe that's called H, the set of diagonal matrices. And it's isomorphic. F squared. Okay. So now let's study this Jacquet factor. So it flows from representations of G into representations of H. But you may also view it as representations of B, which are trivial on U. Okay. So our first lemma today says that the dimension of Jacquet factor of the induced representation, like here, is exactly 2. So the Jacquet factor is sort of like restriction. It's not exactly restriction as you see, but it plays the role of restriction. More precisely, it would be called parabolic restriction. So you start from a character of this diagonal group. Yes, this mu is the character of the diagonal group, and then you extend it to the character of Borel and then induce. So it's called a parabolic induction from diagonal Cartan to the whole GL2.
And it doesn't matter here if mu1 is equal to mu2 or...
Absolutely, for any, this is true in general for arbitrary mu. As I announced, the other claims will be true only for general or special mu's. Okay, so once again, in a sense, those two factors play the role of induction and restriction, and in order to study the induction, we first study the restriction. Okay, so this is just by definition. So what is the induced space V? I don't know. I mean this the induced. By definition, this is the space of functions from G to complex numbers, because we induce from one-dimensional representation. This one-dimensional representation, such that f of B G is mu of B times f of G. Oops. Okay, and now we take the coinvariance or invariance. So let's take invariance, and JV will be equal to the space of functions from F to from G to complex numbers, such that f of BG is equal to mu of B f of G. But the action of G is on the right, so f of GU is equal to f of G. Right? That's just condition of being an U invariant. Okay, but now recall the Briard decomposition. Sorry. Namely that the whole of G is B, disjoint union with B, W, U. Okay, and then you see that this space is necessarily two-dimensional, because this condition defines your functions uniquely on double cosets of B and U, right? So we can write down a basis in this Jacquet space, it consists of two functions. F1 of 1 is 1, F1 of W is 0, and F2 of 1 is 0, and F2 of W is 1. Okay, so lambda is proved. And how do I erase everything? Like this. Yeah, very effective. Thank you. Okay, now the second lemma says that F1 in this Jacquet functor space, two-dimensional vector space, is the eigenvector, or maybe an eigenvector of V that acts on the Jacquet functor with eigenvalue mu1. Sorry, mu. And F2 is an eigenvector with eigenvalue mu W. Okay, and the proof again is just by definition. Just let's compute. So BB is an element in Borel. This is by definition F1 of 1 times B, that is B. 1, I mean, is the identity element in G and G, in GL2. Yeah? And this is, as we know, mu of B times F of 1, F1 of 1. Oh, sorry. Yeah, right. We went by this and evaluate at 1. Now we want to evaluate at W. Evaluate at W. You want to get 0. So this will be F1 of WB. We can by definition it is 1 of WB some U. So for an appropriate U. Okay, and then this will be by our condition mu of V1, F1 of W, but F1 of W is 0, so that's 0. Okay, so we check the first claim. Now the second claim. Is checked approximately the same way. So we evaluate at 1, and this is F2 of B, and this is mu of B, F2 of 1, and this is 0. What is more interesting is to compute a W, and we will compute the evaluation at W, well, separately for values B. So first of all, let's assume that B is diagonal. Okay, H is the set of diagonal matrices. Okay, and then when we compute, we get F2 of W. Sorry. WD, and the W squared is 1, so we can rewrite it as F2 of WD W. But the WDW is the conjugation with W, so it just swaps the entries of diagonal matrix D, and so we get F2 of WD W inverse F2 of W, and well, this is just mu W of D F2 of W. Okay, so we checked what we wanted for diagonal matrices. But now we want to do this for arbitrary matrices. And I press this, yeah, with your benevolence. Okay, and now for general B, let's compute F2. And what we see, certainly, I just raised the claim that the space is two-dimensional with certain bases, and certainly it's some combination of the basic elements. So this is C1 of B times F1 plus C2 of B times F2. Okay, but now, sorry. If we evaluate at 1, we see that C1 of B is 0. Okay, and hence C1 of B, yeah. So the value of our function is 0, so the C1 of B is 0, okay? But then it means that C2 of B is a character of B. But then this character is uniquely defined by its restriction onto H and B, which we already computed. Okay, so our lemma is proved. So now lemma 3. So let V row be an irreducible representation of G. Then the Jacquier functor of V does not vanish if and only if our representation embeds into the induced one. So there exists some character such that V row is contained in the induced representation from B. Okay. So the Jacquier functor is an important device that shows us if our representation is contained in induced or not. Okay, if it's contained in no induced representation, it's what's called cuspidal. So maybe we can introduce this terminology right away. So if row is cuspidal, if the Jacquier functor vanishes, and so V is separated from induced representations. Okay. Now, for example, if we were working over real numbers, then this would make no sense because over real numbers, all the representations have non-trivial homes into or from some induced representations. Okay, but over periodic fields, this works just as stated. So there are some representations that have nothing to do with induced ones, and they're called cuspidal. Okay, so let's prove. This lemma. And the proof is immediate, so we know that since the quotient of Borel group, the diagonal group, is abelian, any representation of this group necessarily splits into characters, into eigens, one-dimensional eigenspaces. So there is a vector V in the Jacquier space such that row of B is just multiplication by some character. Maybe I should say there exists V and a character mu. Okay. And this means that the over Borel, the home space from the restriction from G to B of our representation into mu is not 0, and then by Frobenius, right here, right? No, but I can move it.
Yeah.
So by Frobenius reciprocity,
This is common eigenvalue for eigenvector for any B. Yeah.
yeah, for any B,
Yeah. Okay.
So by Frobenius reciprocity, home from V to the induced representation is not zero. And that's what we wanted. We also wanted the converse statement. Well, if such a home may be in the opposite direction,
But we did prove that when we induce from mu, we get irreducible representation, no?
say again, what do you mean? That when we induced from mu?
That when we induce from mu, we
it's
get irreducible
no, it's not even true. We'll discuss this in a moment, but well, this V is irreducible, but this is something may be reducible, which contains V.
Yeah, okay, V is irreducible. Okay.
V is irreducible, yeah.
Okay.
So if home from the induced representation into V is not zero, then this representation contains an eigenvector. B, what was it? B mu eigenvector, and is generated by this is V. No, not V. What should I call it? E maybe, and is generated by E as a G module. Hence, the image of E in V is also a B mu eigenvector. In particular, it lies in the invariance of U. And it is not zero because it generated the whole induced representation. Okay. So this is proved. And now we are ready for the reducibility claim. That is corollary. First, that any induced representation contains no more, well, not more than two irreducible components. Proof again is immediate, just because we know that the dimension of Jacquet functor is 2, right? So if this reduced representation splits into too many parts, whatever, U1 plus V2 plus so on plus VR, then the Jacquet functor of V, we know the dimension here is 2, but then suddenly it splits in direct sum of all those. But those do not vanish as we just proved. Hence, R is at most 2. Okay. Now, next lemma 4 says that if mu1 equals mu2, so our character of Borel is degenerate. Yeah, it assumes the same values on diagonal elements. Then the induced representation contains a one-dimensional subrepresentation. The proof is again immediate. Well, we just know that mu of B is say B is A C D 0. So mu1 of A times mu1 of D, right? And this is just mu1 of determinant of G, of B, sorry. Right? And now this is well, mu1 of determinant of G as a function from G to complex numbers is B mu eigenvector in the induced representation. Okay, so that's easy. And finally, lemma 5 says that any induced representation contains not more than one-dimensional component. So we know that there are no more than 2 components. Sometimes we have one-dimensional component, but we cannot have 2 one-dimensional components. And well, this follows from here because altogether no more than 2 components. If they are both one-dimensional, then dimension of the induced representation must be 2, which is nonsense. Because in reality it's, what is it, by the way? The dimension of this representation we're discussing.
Q plus
Right.
Q plus
Absolutely, yes. Because it's the number of right cosets of B in G. Okay. So lemma 6. That if we restrict from G to P. Remember we had this subgroup P. A, B, 0, 1. Subgroup of Borel. So when we restrict our induced representation to this mirabolic subgroup, then what we get is, first of all, this Q minus 1 dimensional representation, irreducible representation of P. The unique, the unique higher dimensional representation, not a character. Okay, and we need something two-dimensional, right? Because the dimension is Q plus 1. We restrict it to P. We get Q minus 1 plus something two-dimensional. What is this two-dimensional? How it is? Huh?
Mu1, mu2.
Sort of, yeah. So it's just a restriction from, say, B, if you wish, to P of this Jacquet factor. Yes. Oh, yes, certainly.
Yeah. So we want to prove that induced representation have no more than one one-dimensional component.
Yes.
And how we do this?
Yeah, just because we know that altogether there are not more than two components. So if you have two one-dimensional components, then the total dimension is 2, right? 1 plus 1. But we know that the induced representation has dimension Q plus 1.
Yeah.
So unless Q is 1, yeah, there's contradiction. Okay, so this is Jacquet factor. And we proved a few minutes before that is two-dimensional. Okay, so let's prove this. Well, this Jacquet functor is a two-dimensional B submodule of the induced representation, right? Namely, you take this induced representation and you take its U invariance, and B acts on U invariance. Okay. Now P is a subgroup of Borel, so certainly it acts here as well. Just B being a subgroup of B. Okay. And now take set V, the direct complement of this Jacquet factor in the space of induced representation. Okay. Now the dimension of V is Q plus 1 minus 2, that is Q minus 1. And now know that by definition, sorry. By definition, the action of U in V has no invariance whatsoever, right? By definition of the Jacquet functor, when we take U invariance in V, we get 0. Okay, because otherwise they would contribute to the Jacquet functor, which we know is two-dimensional and it's already taken care of. So there are no invariants, but this means that V must be pi. As P modules. Because we know that all the P modules are either this Q minus one dimensional irreducible pi or the characters, but the characters are trivial on U. Any other P module is trivial on U. So there we are. Now, lemma 7. Sorry. Well, if the induced representation is reducible, then it contains a one-dimensional component, and in this case, mu is degenerate, so it is equal to its swapped. So it's equal to mu1 for some mu1. Okay. So let's prove this. So first of all, if it's reducible, then it has two components. We know, say V plus G prime. Yeah, we proved some minutes ago that there are no more than two components. Those two. And by lemma 6, we can assume that say V equals pi. Well, when restricted to this parabolic subgroup P. Yes.
Does we consider that V is irreducible P representation?
U has no more than two components.
Yes.
No, in lemma 6. Yeah, in lemma 6.
Lemma 6, yes.
We talk about V, the direct complement of G of M hat, and we doesn't consider that V is irreducible P representation.
Well, we proved that it's an irreducible P module.
Yeah, but why it's...
It can either be a sum of one-dimensional or one.
Yeah, we classified all the PP representations,
if it's how it should material.
but too long ago, yeah, like 10 days ago or something like this. And there was just one Q minus one dimensional representation, pi, and all the rest were just characters one dimensional. And they were trivial on U.
Yeah, okay.
Okay, so we can assume that pi well, maybe not. Maybe I'm too fast. Maybe I should say that that V restricted to P contains pi. Okay, not necessarily equal to. Now pi lemma 3. We know that the Jacquet functor of V certainly does not vanish. And Yeah, the Jacquet functor of pi, as we just argued, does vanish. Okay? So we conclude that V contains pi properly. Okay? But then it implies that the dimension of V must be well, strictly bigger than dimension of pi, but strictly smaller than q plus 1. Right? Because the total induced representation has dimension q plus 1. Hence the dimension of V is q, and hence the dimension of V prime is 1. And that's what we wanted to prove. Right? And now for part B, we want to prove that in this case the character is degenerate. So we already know that it contains a one-dimensional component. So we know that the induced representation contains a character, say chi from G to complex numbers, and this chi is well, chi of G is just chi of determinant of G, so to say. And then from the point of view of induced representation, there's some function on G which is left be invariant. Okay, so well, there is a function from G to C such that f of bg equals mu of b f of g, but f of g whatever r equals chi of r f of g, and also equals rg, okay, and then this implies that mu of b equals chi of determinant of b. Okay, so
R is an element of what?
R is an element of G.
Why the second word equals? You know that
Because
here-
just this character, it's a function on G, well, which has this property. We'll say for chi. Yeah, just this character, we view it as a function in the induced representation. So any one-dimensional representation of G is of this form. Now it is embedded into the induced representation. The induced representation is realized in space of functions with this condition. But this function has also this property. Okay? And so the so mu of b must be chi of something, and so it is the diagonal form, degenerate. Okay. Now lemma 8. And this will be, I think, the last lemma for the principal series for induced representations when they coincide. So homomorphisms from one induced representation to another one is non-zero if and only if either mu prime is just mu, which is evident, or mu prime is mu w. So you just swap the two components. Proof. Again, as easy. So assume there is some irreducible representation. The rho contained both in these two induced representations. Okay. Then let's consider the Jacquet factor V, and it's contained in those two Jacquet factors. Well, it's, first of all, it's not zero, and Jacquet factor of V is contained in this, and we know that this is mu and well, plus mu w, and also contained in the Jacquet factor of induced from mu prime, which is mu prime plus mu prime w. Okay, so there is something in common. Okay. So these two have a common component. And this happens only in these two cases. Okay. So the last lemma line says that if mu is distinct from mu prime, then if the induced representations coincide, mu prime is just the slope of mu, and the proof is immediate as always. So if the induced representation is irreducible, then use lemma 7, and if it's reducible, then is reducible, then use lemma 8. Okay, and so
isn't number 7 was about reducible representation?
Maybe I should swap. Sorry. Okay, so now we can formulate the bottom line. of our studies today, that the dimension of induced representation is always q plus 1, that this induced representation has at most two components. That it is irreducible if and only if mu1 is not equal to mu2, so it's sort of generic. If it is reducible then it means that it decomposes into the sum of two, as I promised. And finally, the two are isomorphic. If and only if mu prime is mu or mu prime is mu w. Okay, so it means that we have q minus 1 times q minus 2 over 2 irreducible principal series representation. And q minus 1 characters and q minus 1 Steinbergs. So here dimension is q plus 1, here dimension is q, and here dimension is 1. Okay. Now, well, I have 10 minutes, so maybe let's start the discrete series. Yeah. By the way, let me just say one word about the home assignment. That if mu is degenerate, for example, trivial character, then we are in this case. The induced representation will be will consist of two components, and so its endomorphism algebra will be non-trivial. It will be two-dimensional. Okay, but so on the one hand, from this point of view, it's very stupid. It's just scalars C for endomorphisms of this plus scalars C complex numbers for endomorphisms of that sum, right? Just C plus C, semi-simple algebra. But if you compute it just from scratch, from definition, the endomorphism of the induced representation, then it will be something quite non-trivial, and it's called Ivahori-Heike algebra. Even for GL2, even in the home assignment it is for GLN, but even for GL2, it will be it will have some generator T, and well, it will be commutative, but the relation will be T minus Q times t plus 1 is 0. So you see that this polynomial has different roots, so the corresponding algebra is just c plus c, semi-simple. But the similar relations for general GLN are very important. It's called Ivahori-Hecke algebra. It's on the basis of representation theory of finite groups, Chevalier groups. And so this is what your home assignment is about. Okay. So now for discrete series. And the first lemma here will be, in fact, the first and the last lemma here will be that V rho is cuspidal, meaning that the Jacquet functor annihilates V. So if this is so, then the restriction from G to P, this parabolic subgroup of V, is a multiple of pi. Pi tensor some multiplicity space. So it's a sum of a few copies of pi. Nothing else, nothing one-dimensional things. So in particular, the dimension of V must be m times u minus 1. Well, eventually we'll prove that m is one-dimensional, but the lemma only says that the restriction is proportional to pi, and the proof is that if otherwise the restriction of V to P would have a one-dimensional component where U acts not trivially, trivially. And hence, the Jacquet functor of V, which is just U invariance, would be non-zero. Okay, so this is evident. And now, the proposition says that this multiplicity space is actually one. So maybe I should say it more not in such a short form. So V rho is cuspidal. Implies that the restriction from G to P of V is just pi, and well, the converse claim. So we have 2 minutes, and let's prove the converse claim. Well, pi is irreducible, and implies that certainly V is irreducible. And if V rho lie in the principal series, then we would have of V, either Q plus 1 or Q or 1. But dimension is Q minus 1. Okay. So now I will prove the first part next time, and the proof is well, the proof is as important as the result itself. It's called the Gelfand trick. I mean, if the multiplicity space were higher dimensional, not one dimensional, then the endomorphism algebra would be non-commutative. It would be just over P, over restriction from G to P over V would be matrices R by R. Okay, and non-commutative. For R, sorry. Bigger than. Okay. On the other hand, this endomorphic space can be computed from other point of view, in a sense explicitly, and well, because we know that that's well, okay. So I'll explain it next time. But the endomorphic algebra can be computed, and it is commutative. The commutativity proof is given by Gelfand trick. So you introduce some anti-involution which acts trivial. So it must be commutative. It's very important and ubiquitous in representation theory. So we'll do it next time. And after we do it next time, we'll start the Andreevei representation of symplectic group, which is also very important and ubiquitous for representation theory. So the next time will be very important. Thank you. Yes?
It's symplectic group over FQ. Yeah?
Oh yes, over fine field. So it works over any field, and it has very important applications, especially over adels, so over rational numbers, but also over all local fields. For example, this is one way, like 101st way to prove Gauss reciprocity law from some representation theory of SP2 or SL2. You can deduce Gauss reciprocity law. Okay, thank you.
To z czego to nas
Okay, thank you.